afternoon, everyone. Today, our group will present about the comparison between LDPE and HDPE. First, let me introduce polyethylene. Polyethylene is a synthetic polymer comprising ethylene molecules, and it is one of the most widely used plastics in the world. In terms of characteristics, polyethylene is lightweight, has good chemical resistance, and is both flexible and durable. Water resistance, a good electrical insulator, and easy to process and manufacture. Because of these properties, polyethylene is commonly used in everyday products such as plastic bags, containers, and bottles. Now, let's look at why this topic is important. First, LDPE and HDPE are widely used in many daily products and industrial applications, so understanding them is very relevant. By understanding the differences between LDPE and HDPE, manufacturers can choose the most suitable material for specific uses. Third, their properties directly affect product performance, flexibility, durability, and cost. Lastly, studying these polymers also helps improve product quality and support sustainability, especially in terms of material efficiency.
Today, I will explain the key chemistry concept behind two types of polyethylene, which are LDPE and HDPE. Both of these are polymers made from ethylene differ in their molecular structure, and this difference affect their physical properties. Firstly, LDPE or low-density polyethylene has a branch structure. Due to this, things cannot pack closely together. As a result, LDPE is closely packed, has a lower density, and is soft and flexible. This is why LDPE is commonly used in flexible packaging materials. On the other hand, HDPE or high-density polyethylene has a straight chain structure with very little branching. This allows chains to pack close together. Therefore, HDPE is tightly packed, has higher density, and is strong and rigid. This makes it suitable for products such as bottles and pipes.
As we just learned, the difference between these two plastics isn't what they are made of, it's how they are built. Before we dive into the items you'll find in a typical kitchen or garage, let's bridge the chemistry to the real world. LDPE's branch structure. Because those chains are messy and loosely packed, the material stays soft and stretchable. HDPE linear structure. Because those chains are ordered and tightly packed, the material becomes dense, taut, and rigid. Because LDPE is so pliable, we rely on it for items that need to move, stretch, or seal. For example, squeeze bottle. Take a cube mayonnaise bottle for example. It needs to deform easily under pressure and then pop back into shape without cracking. That's the loose molecular structure at work. Cling wrap. For food storage, we need high elongation. LDPE's branched chains allow it to stretch and cling tightly to the containers, creating an effective moisture barrier. Coffee cup lamination. Paper cups are naturally porous. To stop your latte from soaking through, we apply a thin internal coating of LDPE. It's heat sealed to the paper, providing a waterproof lining that won't flake off when the cup is bent or handled. The job requires heavy-duty durability. We turn to the tightly packed chains of HDPE. Recycling bin. These live outdoors and must endure UV rays, heat, and freezing cold. HDPE's high density makes it rigid and chemically resistant, ensuring it doesn't degrade from waste or harsh cleaning items. Milk jugs. These have to stand upright and support the heavy weight of the liquid inside without buckling. HDPE has an incredible strength to density ratio. It's tough enough to hold the milk, but light enough to carry easily. Hard hats. In an industrial setting, gaffiniers need extreme impact resistance. HDPE is tough enough to absorb significant energy without shattering, yet it's comfortable enough for a worker to wear all day. So, the next time you're squeezing a sauce bottle or tossing a jug into the recycling bin, remember you're feeling the difference between a branched and a linear molecular chain.
First, for HDPE, its main advantage is that it is strong, which makes it ideal for products that need to hold their shape under pressure. LDPE, on the other hand, is flexible and transparent, so it is perfect for plastic films and clear packaging. Next, for the disadvantage of HDPE is that it is opaque. That means it will block light, so you cannot use it for any application where you need to see through the material. For LDPE, the disadvantages are twofold. First, it melts at a lower temperature, so it is not heat resistant. Second, it tears more easily under heavy loads, which limits its use in heavy-duty applications. Looking ahead, the industry is moving heavily toward closed-loop recycling, where plastics are recycled back into the same type of product again and again. Here is some good news. The good news is that HDPE is easily recycled in standard municipal bins. Most cities accept HDPE containers with the number 2 recycling symbol, so it fits well into that future. However, both HDPE and LDPE have a major environmental drawback as they degrade very slowly in nature. This causes long-term environmental challenges as it will break down into microplastics that harm wildlife and ecosystem in nature. The problem is even worse for LDPE because LDPE is often used as thin film or flexible packaging. It frequently tangles in recycling machine. This creates major recycling bottlenecks.
Alright, to bring everything together, I will be summarizing the core takeaway from our presentation. As my group highlighted, the physical properties of a polymer depend entirely on its molecular architecture. Even though both plastics are made from the exact same chemical ingredients, carbon and hydrogen, it is their microscopic differences that dictate the IBD use. To recap, HDPE has a linear structure that makes it rigid and strong, which is exactly why it is chosen for high-strength applications like pipes and heavy containers. On the other side, LDPE has a branch structure that keeps it soft and flexible, making it the go-to material for products like plastic bag and transparent film. The ultimate takeaway from this comparison is the sheer power of polymer chemistry. By understanding how these molecules are arranged, scientists can engineer this basic element to solve vastly different real-world problems across medicine, industry, and our daily life. That's all from us. Thank you.